So nuclear decay occurs when the nucleus of an atom is unstable and spontaneously emit energy in the form of radiation, and it is also called radioactive decay. Nuclear decay has different types, naming alpha decay, beta decay, electron capture, gamma emission, and positron emission. So let's have the alpha decay. So first type of nuclear equation is the alpha decay. So in alpha decay, let's remember that it has 2 protons and 2 neutrons, and it has the general formula of helium 4 and 2, or simply known as alpha. For an example, let's have the unstable nucleus of uranium with atomic mass of 238 and atomic number of 92 will undergo alpha decay. So let's copy again uranium 238 with atomic number of 92. Draw an arrow, and on the right side, let's have plus with alpha decay, which is helium 4 and 2. So in able to find the new element after the alpha decay, we must subtract the 238 and the 4. So the answer will be 238. And next, the atomic number. 92 minus 2 is 90. So the new element is thorium. So in able to check if it is equal, we must add in the right side 234 and 4 will be 238. So it is equal. Same goes with the atomic number. Let's add 90 plus 2 is equal to 92. Another type of nuclear equation is the gamma decay. Gamma decay is considered as the most easiest way of nuclear equation because it has a pure energy. It doesn't have any mass or charge, and gamma decay doesn't change at all. For an example of gamma decay equation, an unstable nucleus of thorium with atomic mass of 234 and atomic number of 90 will undergo gamma decay. So again, let's copy thorium with atomic mass of 234 and atomic number of 90. Draw an arrow, and first let's write the addition sign and the gamma decay equivalent, which is Y with 0 atomic number and atomic mass. And let's proceed to subtraction. Let's subtract the atomic mass of thorium and the gamma decay, and the answer is still 234. Same goes with the atomic number, and still the answer is 90, and the answer is still thorium. Another type of nuclear equation is the positron decay. So in positron decay, the proton being loosed will turn into neutron. And positron decay, generally known as beta with 0 atomic mass and 1 atomic number. For an example, carbon 11 with atomic number of 6 will undergo positron decay. So again, let's copy carbon 11 6 and draw an arrow. But remember, we must find the new element. But first, write the plus sign and the general formula of positron decay, which is beta with 0 mass and 1 atomic number. So in able to find the new element, we must subtract the 11 and 0, which is the atomic mass, and the answer will be 11. Next, same goes with the atomic number of carbon to the positron decay. 6 minus 11 is equal to, yes, 5. So after that, the new found element is argon. So enable to find out if the equation is balanced, let's first see the atomic number and atomic mass if it is equal. So if it is equal, the nuclear equation is balanced. Another type of nuclear equation is the electron capture. So in electron capture, always remember that the atomic mass doesn't change at all. Though the atomic number decreases 1. And it has a general form of electron with 0 atomic mass and -1 as the atomic number. For an example, let's have the potassium with atomic mass of 40 and atomic number of 19, and plus the general formula of electron capture, and copy the arrow, enable to find the new element after the electron capture. Let's add the atomic mass 40 and 0. So the answer will be still 40. Then next is the atomic number. 19 plus -1. The new atomic number will be 18. So the new found element will be argon. And don't forget to write the gamma ray, which represent the extra energy being released during the electron capture. To check if it is balanced, if both atomic mass and atomic number are equal to each other, it is balanced. So let's have another example of electron capture. But this time we have to determine the origin element after the new element has been captured using the electron capture. So the new found element is magnesium. So next, let's copy the general formula of electron capture and copy the plus sign. So unable to find the origin element, we have to subtract the atomic mass, and since the atomic mass never change, let's subtract the atomic number, and the answer will be 13. So the origin element before the electron capture is aluminum plus the gamma ray.
And lastly, the beta decay. So, in beta decay, let's remember that the neutrons being loosed during the process will turn into protons. And protons emits beta particle during the process. Let's proceed to example. So, carbon with atomic mass of 14 and atomic number of 6 will undergo beta decay. So again, let's copy carbon with atomic number of 6 and atomic mass of 14. Draw an arrow, and on the right side, let's write the plus sign with the beta decay general formula. So in able to find the new element, let's subtract the atomic mass of carbon to the atomic mass of beta decay. So 14 minus 0 is still 14. Same goes with the atomic number of carbon, and the answer will be 7. So the new found element will be nitrogen.
So let's check if it is balanced. So first, let's add the equation in the right side. 14 plus 0 is 14, so it is balanced. Next is the atomic number. 7 plus negative 1 will be 6. So it is balanced. So in order to measure your learning regarding with our topic today, let's have the assessment. So complete the following equation using the correct nuclear equation in every problem. Good luck, everyone!
Hello, welcome to Modern Physics. This is Ms. Chashami Mata. Topic objective: explain the concepts of activity, decay constant, and half-life of a radioactive sample. What is activity? Activity in radioactive decay processes the number of disintegration per second or the number of unstable atomic nuclei that decay per second. Activity is determined by counting with the aid of radiation, detectors, and electronic circuits the number of particles and protons ejected from a radioactive material during convenient time interval. Activity is expressed in the International System of Units by the becquerel, abbreviated BQ, which is exactly equal to 1 disintegration per second. 1 becquerel is a very small amount of the radioactivity. For example, household smoke detectors typically contain 0.3 micrograms of the radioactive isotope americium-241, which emits about 37,000 becquerel. The old standard unit was the Curie abbreviated CI, and which is equal to 3.7 times 10 raised to the power of 10 becquerel. What is decay constant and half-life of a radioactive sample? So first, the decay constant. Decay constant determines the rate of decay and denoted by the symbol lambda. The radioactive decay law states that the probability per unit time that a nucleus will decay is a constant, independent of time, that is decay constant. Lambda is defined as the natural log of 2 divided by the half-life, where natural log of 2 is equals to 0.693147. Example, plutonium-239 has a half-life of 24,100 years. What is lambda? Lambda equals to natural log of 2 divided by 24,100 is equals to 0.693147 divided by 24,100. Lambda is equals to 2.876 times 10 raised to negative 5. It is a unit, other commonly used units, and mathematical expressions. Next, the half-life. The interval of time required for 1/2 of the atomic nuclei of a radioactive sample to decay, or equivalently the time interval required for the number of disintegration per second of radioactive material to decrease by 1/2. To find half-life, half-life equals natural log of 2 divided by decay constant. Example, tungsten-181 has a decay constant value of 0.005723757 per days. What is its half-life? Half-life is equals to natural log of 2 divided by decay constant is equals to 0.693147 divided by 0.005723757 is equals to 121.1 days. The formulas used in calculations involving the exponential decay of radioactive materials.
Hello everyone, in this video we will talk about nuclear fission and nuclear fission. So let's get started. Nuclear fission is the splitting up of a large and unstable nuclei into a smaller nuclei. At the same time, it releases loads of energy, which is how we get all of our nuclear energy here on Earth. Nuclear fission can occur in two different ways, either spontaneously, where the fission is unforced and happens all by itself, or by absorbing a neutron, which is effectively splits a nucleus by making it even less stable. In practice, spontaneous fission is rare, and so when we use fission and nuclear reactors, we have to use neutrons to get process started. To properly understand how the process works, let's go through steps. As we said, we start off a large unstable nuclei like uranium-235 and refire are relatively slow-moving neutrons, answer his addition of a neutron to the nucleus make it even less stable and causes it to split apart into two smaller nuclei that we call daughter nuclei. It also releases 2 or 3 more neutrons and importantly, loads of energy in the form of gamma radiation. Each of the neutrons can they go on to repeat the process all over again. With another uranium nuclei and so more nuclei, energy and neutrons will be released the wait again allows the process to start over. Now, the key point of this process is that nuclear fission leads to a chain reaction where the first fission can trigger more fission, where it can turn to even more efficient and so on. If this process isn't controlled properly, then the whole system can quickly get out of control and release huge amount of energy, which is exactly what happens in nuclear bomb. Nuclear fusion, which is when 2 lighter nuclei join or fuse to form a single larger nuclear. For example, 2 hydrogen nuclei like hydrogen 1 and hydrogen 2 could fuse together to form a helium-3. This process releases absolute tons of energy, and it is the process that fuels stars. It's also how all elements heavier than hydrogen were made. The reason fusion produces such large amount of energy is that because some of the mass of the original nuclei. In this case, 2 hydrogen is being converted to energy, rather than transferred to a new helium nucleus. You can tell this from looking at the mass number, but I just trust us that a helium nuclei will be very slightly lighter than a total mass of the 2 hydrogen nuclei. You don't need really to calculate this energy in any way, but out of interest is converted by Einstein's famous equation E equals mc squared, which tells us that you multiply the mass that being lost by the speed of light squared to work out how much energy you will be converted to. And as the speed of light squared is around 10 times to the power of 16, you can see why a lot of energy is released. Another great thing about nuclear fusion is that it doesn't produce any radioactive waste, and we can easily make the hydrogen that's needed as a fuel. The issue though is fusion only happens at really high temperature and pressure, as in 10 million degrees Celsius. Because of this, we can currently do nuclear fusion here on Earth. But there is a lot of experimental research going into discovering how we could do it on